Hi everyone, and welcome back to Everything is Relative with me, Mr. K, where we'll be doing some problem solving on the topic of nuclear physics for CAIE or Cambridge A-Level Physics 9702. Now, I've taken a random selection of past exam questions and put them together in the hope that these questions cover the entirety of the topic, at least most of it, and gives you some experience with a wide range of problem solving. Now, there are many questions and we can't tackle all of them, but we'll try to cover at least the most important concepts in the topic at least once. So the first question we have is from November 2009. This is paper 4.1 and it's question 8. So again, you'd see that these questions are quite late on in the paper, since this topic is later on in the syllabus. So this question says the control reaction between deuterium, which is H2, and tritium H3 has involved ongoing research for many years, and the reaction is given. We have deuterium and tritium undergoing a fusion reaction, this is nuclear fusion, producing helium-4 plus a neutron plus Q. It tells us here that Q is an energy, 17.7 mega electron volts. It turns out that this energy is the energy given to the neutron. It's kinetic energy given to the neutron after the fusion occurs. It's a common type of fusion reaction, and we are then given a table of the binding energies per nucleon. That for deuterium, that for the neutron, which is blank, which is 0, and that for the helium nucleus. And we can see that the first question is quite obvious. Suggest why the binding energy per nucleon for the neutron is not given. Well, think of the term binding energy. Well, binding energy basically is the energy that is required to bind together the nucleons in the nucleus, the neutron being one of them. But this is a free neutron. It's a single particle, it's free, it doesn't need to have a binding energy. It cannot have a binding energy because it's not in the nucleus. And so simply we can say that the neutron is a single free particle. And so you don't expect the neutron, or a free proton for that matter, any free particle to have a binding energy. It's in the name, binding energy. And then, common type of question, calculate the mass defect in kilograms, however, of the helium-4 nucleus. So how do I find the mass defect? Simply in helium, not in the process. Okay, so I have to find the mass defect delta M. But I know Einstein once said that E is equal to mc squared. The mass defect is the mass equivalent of the binding energy. So I need the binding energy to be divided by c squared. Now binding energy is the nucleon number A multiplied by the binding energy per nucleon. If I'm dividing the binding energy by the nucleon, by the number of nucleons, and then multiplying it by the number of nucleons, I simply get the total binding energy for the helium-4 nucleus. I then divide that by c squared, and what do I get? Now these values are known. I have 4 nucleons in helium-4. Each nucleon requires of 7.07 to place into the nucleus or to remove from the nucleus. So that's 4 times 7.07 divided by c squared. But we know that c squared in mega electron volts is 934. And so this becomes 0.03 atomic mass units. The measurement, though, is asked for in kilograms, so I have to convert atomic mass units into kilograms. I used the form of c squared as 934 mega electron volts for every atomic mass unit. This can be shown. In fact, later on we will show where we get this. And so I have to get rid of the U by going to my data sheet and looking that 1 atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms. And so what am I left with? I put this into my calculator and I get 5.026 times 10 to the minus 29 kg. But let me take a brief look at my problem. I'm given mass defects in three significant figures. In fact, all of the given information is in three significant figures in this problem. And so my final answer should be to three significant figures. And so I'll write it as 5.03 times 10 to the minus 29 kg. And so that's how we find the mass defect, by remembering that the mass defect is simply the mass equivalent of the binding energy, the amount of energy that is required to keep the nucleons in the nucleus. The difference in mass between the complete nucleus and the free nucleons. That is, by definition, what mass defect is. Check out my video that does the crash course on nuclear physics if you're still a bit hazy on the details. Next part of the question, part C, says state the name of the type of reaction that is illustrated by this equation. Let's go back and look at this. This is the equation. Now, by looking at this reaction equation, I see that two light atoms, two hydrogen atoms, two hydrogen isotopes, form a slightly heavier nucleus, that being helium-4. We know that when light nuclei fuse to become a heavier nucleus, in the name, this is nuclear fusion. But since I'm a physicist and I'm lazy, I'm simply going to write fusion. It's good enough to say fusion. So it's nuclear fusion occurring. Two light atoms fusing to become a heavier one. Now, the next part says determine the binding energy per nucleon in MeV of tritium. Okay, it's preferable to always use MeV unless otherwise specified, mega electron volts. So I'm going to do this the long way. I'm going to do it a bit slowly, but by the end of it, hopefully, it should make sense. So I'm going to first look at the energies on the left-hand side of the equation. Let's rewrite this equation just so that we have it in front of us. So I have deuterium, H2, plus tritium, H3, fusing to produce the helium-4 nucleus, plus a neutron, which is given a significant amount of energy, Q. And I know that Q is 17.7 mega electron volts. So on the left-hand side of this equation, the energy is the binding energy, the total binding energy for deuterium. I'm only given the binding energy per nucleon, 1.12 mega electron volts. But I'm looking for the total energy. Okay, I know the question is asking for energy per nucleon, but we'll do that later on. Let's first conserve energy. And so, two nucleons in deuterium times the binding energy for each nucleon, 1.12. We're working in mega electron volts, so I won't write down the units, plus 3, since there are 3 nucleons in tritium, times what we basically want to find, the binding energy per nucleon of tritium. I'll call it X, so we know we need to solve for X. Okay, nothing else on the left-hand side. Let's switch our attention to the right-hand side. On the right-hand side, the energy, ER, I'll call it, is 4 nucleons times the binding energy per nucleon, which from our table was 7.07. 7.07 mega electron volts. The neutron does not have a binding energy per nucleon, so we can write that down. We don't have to, but we can write it as 0. Now, there's the value Q, 17.7. But is it plus or is it minus? Okay, so we can think of this in two ways. Or I'm going to describe at least two ways that we can think of this. Firstly, we can see that on the right-hand side, we know the binding energy is going to be higher. It's always going to be higher. And the reason for that is that's the entire purpose of fission and fusion reactions. With a higher binding energy and a higher binding energy per nucleon, the products will always be more stable than the reactants. And so this 17.7 mega electron volts has to be negative in order to balance the energy. But we can see that as well. We can observe that 2 times 1.12 plus whatever 3 times x is going to be less than 4 times 7.07. And so in order for the equation to balance, this has to be a negative sign. We can think of this in terms of, well, we call all binding energies positive. What is a binding energy? It is the energy required for us to take these two nuclei, the tritium and the deuterium, push them together so strongly, in fact, that the two nuclei fuse and form one nucleus, the helium-4 nucleus. In that process, a neutron, which I'm just going to draw a box around, a neutron is released, and we give that neutron some energy. So the binding energy is the work that we need to put in to allow the fusion to happen, to fuse a nucleus together or to pull nucleons out of a nucleus. But any energy coming out goes the opposite way. And so the reason we have a minus sign is you can think of it as the energy in the opposite way, energy leaving the system in the form of kinetic energy, in the case of the neutron, and that's why we have a minus sign. If all the binding energies were negative, as they sometimes are represented, then this would be a plus. The signs would change. And so we can also know by simply realizing that for fission or fusion, binding energy is greater on the right-hand side. And so that has to be a minus to conserve energy. And so now we can equate the two sides. We can say that by the conservation of energy, 2.24, which is 2 times 1.12, plus 3x is equal to, no extreme mathematics is required to know that 4 times 7.07 is 28.28 minus 17.7. All of these again are in mega electron volts. And with some quick math, we get this to be 2.78 mega electron volts for every nucleon. It turned out that X was already measuring binding energy or energy per nucleon. And so this is simply, again, three significant figures, 2.78 mega electron volts. So we have to be very careful for these kinds of problems. We have to understand what's happening. Fission and fusion will always have a higher binding energy on the right-hand side so that the products are more stable than the reactants. Okay, so that's the end of that question. Let's go back and have a look at where the marks were allocated. So the first question suggests why binding energy for the neutron is not quoted. Simple. For everything that you stated, you get 1 mark. So that's a 1 mark question. To calculate the mass defect, this was a 3 mark question. So I prefer to do the algebra first and then the arithmetic, basically rearranging the equations and then putting in my values. This is to limit the errors that I could possibly make and also to limit the amount of work that I need to do. But again, it's completely up to you. By stating our good friend Einstein, we get a mark E is equal to mc squared for correct substitution and getting a binding energy in joules, which I didn't do, but if you did, you would get another mark for correct substitution. And obviously for the accuracy of the final answer, including significant figures, we get the 3rd mark. And so that's where 3 marks are allocated. Again, that may change, but the idea would still be the same. For question C, state the name of the type of reaction that is shown by this nuclear equation. Simply fusion, spelled correctly. Make sure your spelling is correct and your writing is legible. For part 2, determine the binding energy per nucleon. This is the last sub-question. Making sure you have a minus sign on the 17.7 is very important. Getting the conservation of energy equation correct is also very important. And then an accuracy in the final answer rounds off the 3 marks. Now, granted, you could have done this in much fewer steps with much less writing, but I wanted to illustrate how we went about solving the problem and not just finding an answer. Okay, and so that gives us all our marks for that question. Okay, I hope that was clear. So feel free to go back, attempt the problem for yourself, and come back to these solutions once you're done. Make sure that you aren't taking a sneak peek here and there. Solve the problem, get it wrong, get confused, come back and figure it out with me step by step. The next question is from 2013, October-November exams 2013, paper 4.1. Again, it's a question 8. And like as usual, Cambridge questions, the first part or sub-question is always state, explain, describe, or define, actually, something along those lines. State what is meant by nuclear binding energy. We've been talking about it all this time. And if you go back to your textbook, you have a very good memory, as you should, if you're studying physics. It's the energy that is required to separate the nucleons. Remember, we want to separate, English is failing me, to separate the nucleons that are in a nucleus, but not just to separate them, but to separate them to infinity. To infinity in this case means to literally take each of the nucleons and remove them from the nucleus. That's the total binding energy. How much of energy do I need to input to get all of the nucleons, all of the neutrons and protons inside a nucleus out? Once I've removed all of them, the energy that I've exerted is the nuclear binding energy. The energy of the strong force, the strong nuclear force. Now I'm shown a graph, and I'm told that the variation with the nucleon number A, of the binding energy per nucleon, BE, be careful, it's not binding energy, but binding energy per nucleon, is given in this figure. And I am told rather, when uranium-235 absorbs a slow-moving neutron, one possible nuclear reaction is the following. So uranium-235, which is quite stable, in fact, is slapped with a neutron and becomes uranium-236, which is not as stable. How stable would you be if you were slapped with a neutron? In the process, when uranium-236 undergoes nuclear fission, it becomes molybdenum-95, lanthanum-139, 2 neutrons are released, and 7 beta particles, 7 electrons, with some energy given to the neutrons and the electrons. What is the type of nuclear reaction that's represented by this? Well, I may have never seen this reaction before, but I know that a heavy, clunky nucleus, unstable after being hit with a neutron, splits and forms smaller nuclei that will be more stable. Not completely stable, but more stable than the uranium-236. So, again, since I'm lazy, I'm not going to say the word nuclear, but this is fission, the opposite of what we saw before. Heavy nucleus splits into 2 smaller nuclei, which are roughly the same size. You can see, well, there's a significant difference, but again, they're about half the size of the uranium-235 atom, and they are more stable. Energy is also released in this process as it was for nuclear fusion, and that's why we use fission for nuclear power stations and the nuclear reactors. So what does the graph have to do with all of this? This graph is familiar. You would have seen it often. On figure 8.1, mark the position of the uranium-235 nucleus, the molybdenum nucleus, and the lanthanum nucleus. Okay. let's first mark the uranium-235 nucleus. I'm not given any numbers. I'm not given a scale. So obviously, this is a bit of a thumbs up. It's a bit of an estimation. Where's the uranium-235 going to be? Uranium-235 can't be that stable. All I need to do is throw a neutron onto it and it becomes unstable. So it's going to be a heavy nucleus, and it's going to be towards the end of the graph. So I'll just draw an exaggerated dot, and they ask us to label this position simply U. So this is where uranium is on a curve of binding energy per nucleon against nucleon number. Next, I need to find molybdenum and lanthanum. Let's start with molybdenum, MO. The nucleon number is 95 and is much greater for lanthanum, which is 139. I know molybdenum is not as stable as iron. Iron will be the peak on this graph. So if I find the peak of this graph, this is not asked of you, so there's definitely no need to do this. I just want to illustrate. It's definitely going to be to the right of iron. Uranium splits, becomes two more stable nuclei, and stability is where the binding energy per nucleon, Be, is the highest value. So we're moving leftwards on this graph. That's what fission does. Fission takes us towards the left-hand side of this graph. Fusion takes us up the initial part of the graph. When two light nuclei fuse, takes us towards that binding energy of iron, the holy grail of binding energy per nucleon. So molybdenum is lighter than lanthanum, but it's going to be heavier than iron. And so it's going to be to the right of the peak, and I don't want it to draw it too far. I'm going to draw it somewhere here, slightly to the right of the peak. I'm going to mark that point MO. That's my molybdenum nucleus. And lastly, lanthanum. So lanthanum has a higher nucleon number, has to be to the right of molybdenum, but also needs to be to the left of uranium and cannot be closer to uranium, because then the fission wouldn't happen. So it's actually going to be fairly close to the molybdenum. And so lanthanum, La, we're not too far along from molybdenum, but quite far along from uranium. If you're any closer to uranium, this fission wouldn't occur. This fission wouldn't be possible energetically. And so there are our 3 points: molybdenum, lanthanum, and uranium. And so we aren't done with the question just yet. Goes on to say, I'm going to give you some of the masses of these particles in the nuclei. We're given in atomic mass units, the mass of the beta particle, the neutron, proton, uranium-235, molybdenum-95, and lanthanum-139. Okay, so for this reaction, they want us to calculate the change of the rest mass in atomic mass units. What does that mean? Change simply means find the mass of the right-hand side, find the mass of the left-hand side, and subtract the two. Remember, we have a heavy atom becoming lighter ones, and that's how we know it's fission. So let me find, now I know that the mass on the left-hand side is probably going to be bigger. Let me find the mass on the right-hand side. Simply, it's the mass of lanthanum. The mass of the molybdenum, the mass of the molybdenum atom is given to be 94.945 plus the mass of lanthanum, given in the table, 138.955, many significant figures here, plus, what else do we have on the right-hand side? Molybdenum, lanthanum, 2 neutrons and 7 electrons. Okay. 2 times the mass of a neutron is given to be 1.009 plus 7 times the mass of an electron, which is tiny, the beta particle, 5.5. Remember, beta particles are simply fast-moving electrons. 5.5 times 10 to the minus 4. not fast enough that their masses are relativistic, so we can still use their regular masses. And let's calculate this. And if we put this into a calculator, we get this to be 235.922. That's in atomic mass units. Let's find the mass of the left-hand side. Again, I'm doing this in a very drawn-out manner, which you don't need to do. But as a first practice, it's good to see how questions are solved. Left-hand side is a lot easier. I have uranium and a single neutron. The uranium atom, the mass is given, 235.123, and one neutron which has a mass of 1.009. Aha! So if I calculate this, I get 236.132. Now I want to find the change in mass, which I'm going to call delta M, and that's the bigger number, 236.132 minus 235.922, and I get this to be 0.21 atomic mass units. So it turns out that my change in mass is 0.21 atomic mass units. So quite a bit of working, but in fact, I didn't need to write down everything I did. I could have simply just put all these values into a calculator, found the mass on the right-hand side, done the same for the left-hand side, and found the difference. It was only a 2-mark question. Again, how we actually get there is important. Once we learn the method, actually solving these kinds of problems become easier. Next, we want to know how much of energy is released to 3 significant figures. Very specifically, they told us the number of significant figures we need to use. So we don't have a choice in this matter, but to pay heed to that. So what do? I'm going to go back to the one thing I know about energy. The one thing that I learned about energy in this topic is that E is equal to mc squared. How does this help? Well, I know m, the change in mass, is 0.21 atomic mass units, U, multiplied by 934 mega electron volts for every atomic mass unit, which is 196.14 mega electron volts. So the difference in mass on both sides of the equation will be released as energy. If there's a mass difference on 2 sides of a reaction equation, that difference must be equivalent to an E is equal to mc squared amount of energy. This is quite simple for a 3-mark question. Remember, this value 934 is not obvious. It's not something that you are required to remember. So where did I get this from? I'm going to show you how we can find this. It's basically the energy associated with 1 atomic mass unit. So if I use the same equation, E is equal to mc squared, m is 1 atomic mass unit, and we know that this is 1.66 times 10 to the minus 27 kg for every atomic mass unit U. Then I'm going to multiply this by c squared, which is the speed of light, 3 times 10 to the power 8 meters per second squared. And then I get an energy in joules. Kilograms times meters squared per second squared gives me an answer in joules. That's great. But I want an answer in MeV, mega electron volts, for every atomic mass unit. So what I'm going to do is I'm going to divide this value of joules by 1.6 times 10 to the minus 19. Yay, I'm done. No, I'm not. I want MeV, not EV. I want mega electron volts. Mega means I have to divide by further 10 to the power 6. Aha! By doing this, that's when I get 934 mega electron volts. And so every atomic mass unit U has an energy of 934 mega electron volts. That means if I know the mass of something in atomic mass units, if I knew your mass in atomic mass units, I could tell what your rest mass energy would be by simply taking that number and multiplying it by 934. And so my answer that I got was 196.14, but I needed 3 significant figures, and so it turns out it was 196 mega electron volts. Now that in itself didn't look too difficult, did it? But it was quite a lot of work, quite a lot of thinking that went into it before just finding a solution. So that was the last part of the question. That was a fairly long question, in fact. So let's go back and have a look at how we would score the marks for this problem. Let's go all the way back to where it started. State what is meant by nuclear binding energy. And so the first thing we needed to do was to say that this is the energy required to separate nucleons. Great, but this is 2 marks, and so there must be something else. Couldn't just be that straightforward. Infinity is important, to remove the nucleons or take the nucleons out of the nucleus, to break apart a nucleus. So that way our 2 marks would come from. The next part of the question gives us the graph of nucleon number against binding energy per nucleon BE. We are given this reaction involving uranium-235 splitting up into smaller nuclei, and we can see that since the big heavier nucleus splits into smaller nuclei, this is nuclear fission. Again, spelling is important. Do not mix fission and fusion. Those are 2 different words, different spellings and different meanings. Then we had to mark the position of uranium, molybdenum and lanthanum. And so a mark scheme will be very strict about not just placing 3 nuclei, but placing them correctly. The lanthanum can't be shifted too far right, and the molybdenum also can't be shifted too far right or too far left. And so it should make sense. And that's where you'd score 3. Very quickly, you could score 3 marks. It would definitely take you less than 3 minutes. And so you save some time for more difficult problems if you understand this graph, what it means, and how to go about analyzing or synthesizing the information from that graph. The next question gave us the masses of these particles and asked us to find the change in rest mass in atomic mass units U. And so finding the atomic mass of the right-hand side scores you 1. Applying it to this equation correctly, 236.132 minus 235.922, and getting an answer, all of that work scores you the 2nd mark. You have to be very careful to make sure you put everything into your calculator correctly. If you need to come back and double check if and when you have time, by all means do so. And then the last sub-question says the energy released. Now, stating Einstein's relation, E is equal to mc squared, gets you 1. And then which I haven't done here is finding the energy in joules, which is simply the process that I've showed you on the right-hand side, and then converting it to MeV, mega electron volts, and 3 significant figures. The accuracy of the final answer scores you the final mark. Remember, substitution is important. You cannot substitute values into an equation that don't exist. You cannot simply use your own values in an equation. If you have a number in mind, write it down, tell us where you got it from. If it hasn't been given to you, it shouldn't be there, right? So always write things down so that the markers know that these numbers are not being pulled from thin air. Okay, the next question comes from May-June 2014. This is from paper 4.2, and you can see that's a question 9. Again, very late on in the paper. We're told that some water becomes contaminated with radioactive iodine-131, and the activity of iodine-131 in 1 kilogram of water is 460 becquerel. The half-life of iodine-131 is 8.1 days. Definitely moving on to radioactivity now and half-lives. First things first, what is a half-life? Now, a half-life is a time. The word half-life gives this away, so we can write this as the time for the number of undecayed nuclei in a radioactive sample to reduce to half its initial value. So I'm going to write this down. The time for I'm going to use very specific wording to be technically correct for the number of undecayed. Now, there might be a simpler way to write this, but I want to be very correct when it comes to definitions and statements and laws and so on. So try to remember them and write them in a simple way, but in a simple, correct way. So it's not simply the number or half the number of radioactive atoms. It is the time that it takes for half the number of radioactive atoms to be reached. So to reduce to half of its initial or original value. So very specific wording, but I want to be correct with my definitions. Next, we are told to calculate the number of iodine-131 atoms in a kilogram of this water. Aha. So this is going to be a little difficult. Number of iodine atoms is N. I know this, but I don't know if I have enough information to calculate N. I am given the activity though, A. So the first thing I'm going to do is write down the one thing I do remember, the relationship between A and N. A is equal to the decay constant lambda for iodine-131 times the number of particles, number of nuclei, N. But I also remember another relation. Since I don't know the decay constant, I need to replace the decay constant with something that I do know. And what I do remember, or what I can derive if I don't remember, which we'll also do later on, is that the half-life, I'm going to call it capital or uppercase T for simplicity, is the natural log of 2 divided by the decay constant lambda, which means that lambda is the natural log of 2 divided by T. So I can write this as N times the natural log of 2 divided by T. Now things are becoming more clearer because I know the half-life, log 2 is a constant, A is given, I can find N. And so what I do is, with a little bit of mathemagic, I get N is A times the half-life T divided by the log of 2. So the activity is given as 460 becquerel. Becquerel is simply per second, that's an SI unit. The half-life is 8.1 days. Days and seconds are not the same. So 8.1 is not going to work as is. Now take my word for it, one day has 86,400 seconds. This is just something you know as a physics teacher. Don't ask questions, but you can calculate it for yourself. And we divide this by the natural log of 2, which is just a constant. And what I get is, putting this in the calculator, 4.64 times 10 to the power 8 atoms. That's the number of atoms in iodine-131 atoms in this kilogram of water. And since I'm given two significant figures for the number of days, and I'm multiplying and dividing, my final answer needs two significant figures, 4.6 times 10 to the power 8. So this was a bit of a tricky question. But whenever given a question like this and you're not sure where to go, write down the things that you are given. I'm given an activity. I am given a half-life. I can use this information and the expressions that combine the information to end up at a solution, even if I have nowhere to go. Write down all the things that you are given, the information, A is equal to, T is equal to, etc. And write down all the equations that involved A, T, and what you want to find, which is N. Eventually, things will click, wheels will turn, and you will be able to link the equations and the mathematics so that you can solve the problem. Okay, the next one looks a bit terrifying. An amount of 1 mole of water has a mass of 18 grams. Okay. Calculate the ratio of the number of molecules of water in 1 kilogram of water divided by or over the number of atoms of iodine-131 in 1 kilogram of contaminated water. So the ratio of water molecules to iodine 131 atoms. So the first thing I'm going to do is I'm going to calculate the number of molecules, capital or uppercase N. This is the number of moles times Avogadro's number, going back to ideal gases. But remember, the number of moles is the mass of the sample divided by the molar mass of the sample. That multiplied by Avogadro's number looks as follows. The mass of the sample is 1 kilogram. The molar mass is given. 1 mole of water has a mass of 18 grams. So that's 18, I don't want grams or 1 kg, so that's 18 times 10 to the minus 3. And I have to multiply this by Avogadro's number, which is in my data sheet, 6.02 times 10 to the power 23 molecules for every mole. If I calculate this, I get this to be 3.34 times 10 to the power 25. That's the thing I wanted on the top. But the thing I want on the bottom I also know because I've calculated it before. So for this ratio, the thing I want on the top and the thing I want on the bottom are both known. So hooray, I can now calculate the ratio. This ratio is 3.34 times 10 to the power 25 divided by 4.6. We can even add an extra significant figure for the calculation. Just leave it as 4.6 times 10 to the power 8, which gives us a ratio of 7.26 times 10 to the power 16, or to two significant figures as is required, 7.3 times 10 to the power 16. Again, that also depends on the number of significant figures that you carried throughout the problem. This might round down to 7.2 or up to 7.3 as long as you've done your rounding and your mathematics correctly. And so that's where we get the 2 marks. Number of molecules in water is what we really needed to calculate. And so we go back to our basic understanding of ideal gases, understanding of chemistry, and figure out the number of molecules of water, but the number of atoms in iodine 131 has been calculated earlier. So generally your questions will always follow on from each other. So always remember, as a hint, go back to previous questions and see what you've already calculated and if it can be used in follow-up questions. And the last sub-question in this question says that an acceptable limit for the activity of iodine 131 in water is 170 becquerels per kg. Calculate the time in days for the activity in the contaminated water to be reduced to the acceptable level. So basically this water, you wouldn't want to touch it, drink it, use it, etc. until the iodine level is 170 becquerel per kg. But initially, it wasn't 170 becquerel per kg, it was 460 becquerels for a kg of water. The water was unsafe, it was well above 170. So what do? Let's see how long it's going to take. I know the final activity, I know the initial activity. Is there an equation that links the two? Definitely. A is A naught e to the minus lambda t, the radioactive decay equation, the most famous equation, the most important for this topic. What else do I know? I don't know lambda, but I do know the half-life t. It's been given. The half-life of iodine 131 is 8.1 days. So I can say that this half-life is the natural log of 2 divided by lambda. I can prove it if I don't remember it. So this equation takes a different form. This is A naught e to the power minus log 2 times t divided by the half-life, uppercase T. Now I can lineify both sides, the natural log of both sides. I can also get rid of this minus sign. Log of A over A naught is the same as minus log A naught over A. And so I get rid of the minus sign after taking logs. It's because I don't like negative numbers. This becomes log of A naught over A is equal to log 2 times the time it would take for the safe level of iodine to be reached divided by the half-life uppercase T. Means I do a little bit of a calculation and I get T is equal to half-life times the log of A naught over A, all of this divided by the log of 2. Now if I put in my values, look, I want the time to be in days, so I can leave the half-life in days. I don't need to change it. Times the log of the initial activity was 460, the safe activity, which is the activity at this time, was 170. Divide all of this by the log of 2, and I find that this is 11.6 days. And so the time it takes for this sample to have an activity of 170 becquerels per kg, which is the safe amount, is 11.6 days. So I'll have to wait 11.6, maybe 12 days before this water is safe for consumption, at least to be acceptable for use. And that brings us to the end of the question. So this was very different. No longer are we looking at binding energies, now we're looking at radioactive decays. Let's go back and see where we'd score or lose our marks. Firstly, we need to define the radioactive half-life. It is a time. Simply for mentioning it is a time. It is not a number. It is a time. The time for which the number of undecayed nuclei in a radioactive sample will drop to half its initial value. Bringing those two ideas and points together scores you 2 marks. For mentioning it's a time, you get a mark. For mentioning that the number of particles must reduce to half its initial value, you get another mark. The next question is 3 marks to calculate the number of iodine atoms in a kilogram of the water. Linking the correct equations, A is lambda n gets you 1. Correct substitution scores you another, and then accuracy in the final answer, including significant figures, scores you the final mark. 3 marks for that problem. The next one, to calculate the ratio, you scored a mark for finding the top of the ratio, the number of molecules of water, which is something we weren't given, but we could have found. And the second mark is for solving the ratio correctly and making sure your number is a decimal. Even though we use the word ratio, it should never be a fraction. This is physics. The number should always be expressed as a decimal. And that scores you 2 marks. And then the final part of the question, which says calculate the time in days for the contaminated water to be reduced to the acceptable activity. The decay equation, I'm going to use a little plus sign, combined with the half-life expression. Put those pluses together, you have to have those 2 points to score you the first mark, according to the mark scheme. And then, Bob's your uncle, you do a bit of mathematics, rearranging, substitute correctly, scores you the second. Accuracy for the final answer scores you the third. So, very important that I've done the steps, I've done many steps. I've sort of made this a bit more complicated, but I always, like I say, prefer to do the algebra first and the arithmetic last. I find this way sort of minimizes the chance of me putting in a value in the calculator wrong, also prevents me from having very big numbers carry through different steps of mathematics, which becomes a little bit cumbersome and time consuming. Okay, the next question, moving to a much closer paper, is October, November 2022. This is paper 4.3, and it's question number 10. It says carbon-15 is an isotope of carbon that undergoes radioactive decay to nitrogen-15, which is a stable isotope of nitrogen. Now, radioactive decay is both a random and spontaneous process. State what is meant by random and spontaneous. Specifically, state what is meant by these 2 words with respect to the scenario that you're given, with respect to radioactivity, not what you think these words could mean. What does it mean to be random? Well, it means that we can't predict when a nucleus will decay, or if I have a sample of many, many, many nuclei of a radioactive substance, I can't predict which nucleus is going to decay. So what I can say, and there's two possible answers here, what random means is we cannot predict something. But in this context, what is that thing that we cannot predict? We cannot predict when, important word, when a radioactive nucleus, so simply nucleus, will decay, or, I'm going to write or in uppercase, which nucleus in a sample of a radioactive substance will be the one to decay. Aha. So what this actually means is I can sit and look at a radioactive substance. I shouldn't, but if I could, I would sit and look at a radioactive substance and I cannot tell you which one's going to decay next. I can tell you the approximate time that I need to wait between the next decay or between subsequent decays, but I don't know which one's going to decay, and I can't be really accurate with the time at which the decay occurs. It's going to surprise me and be quicker, and then going to be slightly longer, although on average I can say when it's going to occur. So it's a random process. Spontaneous. The word spontaneous may throw you off a bit. In terms of physics, in terms of nuclear physics and radioactive decay, spontaneous means that this decay is not affected by external or environmental factors. So I'm going to say the decay is simply 1 mark. I don't need to write stories about my grandmother's sister's cat's dog, but I just need to make sure that my important points are in. So the decay is not affected by external factors. I can take this nucleus that's going to decay, throw it in the oven, it's not going to affect the decay. I can throw it in the refrigerator, it's not going to affect the decay. That's what spontaneous means. It's not affected by external factors. Okay, obviously this is leading somewhere. Question will never end there, right? A small sample of carbon-15 decays. The mass m of carbon-15 in the sample decreases with time t. So we are given a graph. Figure 10.1 shows the variation with time of the value of log m, and m is measured in 10 to the minus 16 grams. Remember, the log of something has no unit. What's inside the log can have a unit, but the log is simply giving us an exponent, which physically cannot have a unit. It makes no sense. So I'm given a very shaky graph, but this graph is roughly, looks like a straight line that sort of happened upon an earthquake. It's shaky. And the first question says, state how this figure demonstrates that radioactive decay is random. Now I can see that the time between decays varies. Some of them happen more closer together, and some happen further apart. So even though the graph has a shape that I'm sort of used to, it's a bit bumpy. And so what I see is the graph is not a smooth curve. So the radioactivity is happening in a way that is fluctuating. So I can simply, again, 1 mark. I don't need to write a long story. So I can say that the graph is not a smooth curve, or I can simply say that the line, in inverted commas I guess, the line fluctuates. What should have been, had there been no randomness, a lovely smooth straight line is not. Since the line fluctuates, it is a random process. The next question says, draw the straight line of best fit. So there's meant to be a straight line here. I don't think it's difficult to see that this straight line will be definitely not that. I'm going to draw this in red, make it quite thick. Again, you really don't want to make this graph as thick as I have. But basically, you know what a line of best fit is. going to be the line that's the best balance between all the points. Okay, so it may not be as thick as that, but you, with a sharp pencil, would take your ruler. You have to have a ruler if you're drawing a straight line. You have to have a ruler with you at all times. Ruler, pencil, place it so that you balance the line as well as possible and draw a single continuous straight line through all of the points. And so that's 1 mark, and it does say on figure 10.1. Just please don't redraw the diagram. If it says on the figure, use the figure. Okay, so that's that question done. Now it says to show that the decay constant lambda of carbon-15 is given by the magnitude of the gradient. Ooh, wait a minute. Magnitude of the gradient, how do I get lambda from the magnitude of the gradient? Well, I know that this is the mass decaying with time. Mass and number of nuclei, well, they correlate, right? And so the decay equation has the same form. The mass at any time t is equal to the initial mass of the sample. The sample is losing particles, n, and so its mass is also decreasing at the same rate. M is m naught e to the minus lambda t. I'm going to do a bit of mathematics. I'm going to linify both sides, meaning I'm going to take natural logs of both sides. Ln m, and I'm not a mathematician, so I can say ln, but simply ln is the natural log. And so ln n is equal to ln m naught minus lambda t. Why would I do this? Oh, I've got the log of m on the y-axis, and I've got the time t on the x-axis. Oh, I can see log of m is on the y-axis. I've got t on the x-axis. Remember, the form of a straight line is y is equal to mx plus c. That means this minus lambda, I can write minus lambda as plus negative lambda. That's my gradient. I'm going to use the word gradient instead of m. Don't want to confuse m for some other physical concept, or quantity rather. And then what's left is my y-intercept, the log of m naught. So simply put, this is only 1 mark question, but again I'm showing you where or how to go about solving it. So the gradient is minus lambda, but the question, we're doing this in the wrong place, aren't we? So all of this would be transferred to below, like magic. So here we are, where we actually needed to be. We said that the gradient is minus lambda. The question asked for the magnitude of the gradient. I wanted to underline that, that's why I brought us back here. The magnitude of the gradient, therefore, is lambda. What is lambda? It is the decay constant. And so it wasn't as far-fetched as the question initially looked. There may not have been a lambda anywhere here, but I know the equation that relates number of particles, or in this case mass, and the amount of mass remaining after time t, the decay equation. And so the gradient is minus lambda. You have to show us some working, and then that working takes us to the fact that the magnitude of the gradient gives us the decay constant. Well, what does the next question say? Guess what? Use your line to determine lambda. So we're going to have to find a gradient. I don't just want a gradient though. I want the magnitude of the gradient as we described above. I'm going to take the magnitude of the gradient of this line, and I'm going to choose the extreme points. That's simply, again, because I'm lazy. I'm going to take the very end point here and the very end point there. And so here I have a point. Turns out, if I look at this, it works out to y0, this is 11.6 Again, that's seconds, and I'm fine with that. It's an SI unit, and this is 0. And the unit for the y-axis is nothing. It's dimensionless. It's a log of something. And the other point is, turns out that this is, now x is 0, and actually no, this is not the x-axis. Here we have -8, so I have to be very careful. Thought that was the x-axis or the origin, but it's not. It's -8, so that's 11.6 and -8. And above here we have 0. This is indeed 0, as we can see there, and -4.8. So I've chosen these 2 points. Remember, I just need 2 points in a straight line graph and I can find the gradient. Okay, and I've used 2 points that are on my line of best fit, but also very close, so on the squiggly line that was given. So gradient is -8 minus, remember there's a negative sign, 4.8, and divide that by, and all of this needs to be absolute value, 11.6 minus 0. And so what is the magnitude of the gradient? It's simply lambda. It's, if I calculate this, 2.76 times 10 to the -1. Decay constant will be measured per second, which makes sense. Change in y over change in x is a change in something that's dimensionless, no unit, divided by a second. 1 over a second is per second. And so I can write this as 0.28, same thing, 2.76 times 10 to the -1, giving it to 2 significant figures, and the unit is per second. And so that closes out that question. We're then told, and remember in each question we are told what to use very specifically. The next question says use your answer in part 4 to find the half-life of carbon-15. So I have to use lambda. I can't use a different method, okay, especially if a question is just 1 mark. Turns out I know that the half-life is the natural log of 2 divided by lambda. Don't need to prove this. I wasn't asked to prove this. I know it. I'll show later on in a question how to derive this. Log 2 is a constant. My calculator will give me that. Lambda is 0.28. It turns out I get a half-life of 2.48 seconds. Log of a number has no unit. Divided by per second gives me an answer in seconds. And so the half-life of carbon-15 is very short, 2.5 seconds. And to end off this question, we are given the reaction equation. Carbon-15 decays by becoming nitrogen-15, a beta particle and an anti-neutrino. You remember this from particle physics. State and explain how the mass of the products of the decay must compare with the mass of the carbon-15 nucleus. Aha! What do we know about decay processes? These processes always release energy. They have to release energy. Radioactive decay occurs because something is unstable and it wants to become more stable. If you want something to become more stable, energy must be released. So energy is released by the decay. Very important point. But what does it mean? What does it mean about the mass? Well, the release of this energy comes from the decrease in mass. As the mass of the products decrease, there must be an energy that accompanies this so that the energy on either side is balanced and energy is conserved. So what I'm going to say next is that the release of this energy arises from a decrease in mass. And so how do I conclude? I conclude that the mass of the products must be less than the mass of carbon-15, or the reactant, which is only 1. And so the mass of the products is less than the mass of carbon-15. That's the only reactant. So I wouldn't say reactants, I'll just write carbon-15. Okay, so that was a particularly long question. Let's go back and see how we did. A lot of working, a lot of things that may seem a bit abstract, but if you think about it, they weren't really that abstract. They were things that we've seen before. State what is meant by random and spontaneous processes. 1 mark each. We don't need long stories. We don't need your entire life story. We cannot predict when a nucleus will decay or which nucleus will decay. Either of those scores you the mark. What does spontaneous mean? Spontaneous means this decay is not affected by any external factors or by environmental factors. Don't need anything else. That scores you the next mark. Next, we are given the graph of the variation with time of the value of log of the mass for a carbon-15 sample, which is decreasing with time. If it's a sample decreasing with time, it will decay exponentially, as all radioactive nuclei do. So we are told to state how the graph demonstrates that the decay is random. If you said the graph is not a smooth curve or that the line fluctuates, that scores you the mark. There's no other property of this graph that tells us that the decay is random. Then we are told to draw the line of best fit. No surprises, drawing a solid, sharp, straight line that is the best line that balances all the points scores you a mark. Then we are asked to show that the decay constant lambda is given by the magnitude of the gradient. So I did a little bit of manipulation with the equation, albeit in the wrong place, and by this manipulation I then led to the idea that the gradient was in fact minus lambda, so the magnitude of the gradient must be lambda, which we know is the decay constant. A lot of working there for that 1 mark. Obviously, you didn't have to write it in as many lines as I did, but again, showing you how to go about getting your solution. As you practice more, you notice that your time to solve these problems becomes less. Also, the number of lines you use becomes less. Number 4 says, using the line specifically, find lambda. Give a unit with your answer. Well, I have to calculate gradient. I can use any points. I need to use them correctly. Using a correct set of points scores you a mark, and then an accuracy after substitution in your final answer gets you the other, and that gives you 2 marks. Part 5, Roman numeral 5, says use your answer in 4 specifically to calculate the half-life of carbon-15. And well, it's simply 1 mark. So I need to know the equation. I need to take it all the way through an accurate final answer. There's no room for error here at all to score that 1 mark. Then I'm given the decay reaction equation for carbon-15 as it becomes nitrogen-15, a beta particle and an antineutrino. And I need to explain how the mass of the products of the decay must compare with the mass of the carbon-15 nucleus. Now, an explain question requires, well, an explanation requires some words. And I also have to do a comparison. The word compare is important. So I must explain, but I must explain with a comparison. Energy is released by the decay. A very important point. The release of the energy comes from a decrease in mass. So I'm linking energy with mass, which is what the question is asking me for. What does this tell us? What do we conclude, and how can we compare? Comparison will score me the second mark. That means the mass of the products must be less than the mass of the reactants, or the mass of carbon-15. That's where I score the second mark. So explicitly I was told, make a comparison please, and make a comparison of the mass. So simply put, you have to have a statement somewhere there that compares masses. If you don't, you haven't answered the question. And so that question was 2 marks, and that was the last sub-question. So always be careful with your state, explain, define, describe, list, those sorts of questions. Learn your command words and look at the question words very carefully. Could be the difference between scoring 1, scoring 2, or scoring none at all for a question such as this, even though you may understand what needs to be done conceptually. The last question that I have for you is from February-March 2018, paper 4.2, and this is question 13. So it's still quite a late question. First things first, define radioactive decay constant. Slightly more abstract quantity. It is the probability per unit time of a decay occurring. That's it. Higher lambda, higher probability of decay, more radioactive substance. Lower lambda, a less radioactive substance. So it is the probability, since we don't actually know when a decay will occur, the probability per unit time of a decay occurring. Again, probability per unit time. These are very specific words. I'm not using a roundabout way or using my own words or making up a definition from an equation, using the exact definition. Be very careful, reading, remembering, just as important to a physicist as it is in any other science. Show that the decay constant lambda is related to the half-life T subscript half of a radioactive isotope by lambda T half is log 2. So we finally get to derive this equation. What do I know? I know that a substance decays to a final number of radioactive particles n when its initial number is n0, and we multiply that by e to the minus lambda t. Now, when the half-life has passed, the number drops to half the original number, n0 over 2. So n0 over 2 is equal to n0 e to the minus lambda. What we call the time that has passed is the half-life t half. I can say goodbye to the n-naughts. I can also lineify both sides, if such a word exists. It probably doesn't. Ln half, or log half, is minus lambda t half. There isn't a minus sign in the equation above. But what I know from my log laws is that the log of a over b, you can write it down, the log of a over b is minus the log of b over a. That comes from another log law that says log of a over b is log a minus log b. So simply, I can write log of half as minus log 2. And so I get log 2 is lambda t half. Hey, but guess what? That's exactly what I wanted in the first place. Lambda t equal to the log of 2. So I've proven what I've been asked for. Lambda t is log 2. It's nice, I can explain the half-life simply by knowing the decay constant lambda. That was a 2-mark question. Now the next question scares me a bit. It's a lot of reading, okay, and even it's worth 4 marks. I'm told a small volume of solution containing the radioactive isotope sodium-24 has an initial activity of 3.8 times 10 to the power 4 becquerel. Half-life of sodium-24 is 15 hours, and this happens to form a stable daughter isotope. This solution is poured into a container of water, and after 36 hours, a sample of water, which has a volume of 5 cubic centimeters, is taken and found to have an activity of 1.2 becquerel, drops significantly. Assuming that the solution of the radioactive isotope is distributed uniformly throughout the container of water, calculate the volume of water in the container. just reading that equation, reading that problem statement took 2 minutes of my life. Anyway, I absolutely have no idea where to start with a problem like this. So what am I going to do? Let me write down what I know. I know that sodium-24 has an activity, a peak or maximum or initial activity of 3.8 times 10 to the power 4. I'll write the units as well, becquerel. I'm also given a very important piece of information. The half-life of sodium-24 is 15 hours. Just going to leave it in the units that are given for time being. And when I mix the water with the sample of sodium-24 and I calculate the activity of this 5 cubic centimeter sample, I'm going to call this activity AS for the sample. This is 1.2 becquerel. Don't really know where that value will come in just yet. What do I do now? Well, the one thing I don't have here is lambda. So applying the radioactive decay constant is going to be a little bit icky because I don't have lambda and I can't use that equation. But wait a minute. We've done this before. They even asked us to show that. Lambda is log 2 over the half-life. That's from the previous question. See, we said log 2 is lambda t half. Wait a minute. That's the log of 2 divided by 15 hours. So that's log 2 divided by 15 per hour. That's the decay constant. That's a number, and now I know it, which means that I can find the activity of the sodium after this time of 36 hours. So let's say 36 hours has passed. What should the activity be? We know we found an activity of 1.2, but what should it be if I didn't mix the sodium with the water? So A is A naught e to the minus. Look, I understand there may be other ways to answer this problem, but I'm trying to do it as step by step as possible. The initial activity of the sample was 3.8 times 10 to the power 4. This is going to be multiplied by the exponential, or the base, the natural base e to the power minus 36, which is the time t, 36 hours, times the natural log of 2, which I get from lambda. All of this divided by 15. I can leave 36 and 15 in hours because if I convert them to seconds, the conversions will just cancel off anyway. The ratio will remain the same. What I get is 7,200. 7.2 times 10 to the power 3 becquerel. So I started at 3.8 times 10 to the power 4. After 2.5 days, for 36 hours, I should have had an activity of 7.2 times 10 to the 3 becquerel, but I didn't. I mixed my sample with water and I ended up with 1.2 becquerel for a volume of 5 cubic centimeters. What do I know? I know that the activity of the sample is related to the volume of the sample. I have a larger volume, I'll definitely have a larger activity. I'll have more molecules in a larger volume. Seems obvious. So the activity of the sample over the activity of the sodium must be equal to the volume of the sample divided by the volume of the sodium, and or in this case the volume of the water, which is the same as the volume of the sodium because the isotope is distributed uniformly throughout the container of water, so the two volumes are the same. So what I actually want to calculate here is V. So what this means is if I do a bit of mathematics, I get V to be the ratio of the activities A by AS multiplied by the volume of the sample, which is simply 5 cubic centimeters. I know all these values. This is 7.2, and obviously the amount of water is going to be huge. Okay, the amount of water is going to be huge because it did a lot of diluting to go from 7,200 to 1.2. So 7.2 times 10 to the power 3 divided by 1.2 and all of this multiplied by 5 cubic centimeters. Doing this calculation, I get this to be 3 times 10 to the power 4 cubic centimeters. Two significant figures, 3.0 times 10 to the power 4 cubic centimeters. I had to add a lot of water in order to bring this activity down to something that's probably more acceptable. So what it would have been is 7,200, and I brought it down to 1.2 becquerel, and in that process I required 3 times 10 to the power 4 cubic centimeters of water. This is one of those abstract problems. There's going to be plenty of these in your exam. Things that you have never seen before. It's going to test an aspect of your problem-solving ability that hasn't been tested or has been tested less. So the more you practice, the better your skills become. It will be the same if you're playing an instrument, if you're playing a sport. Hard work, practice, makes perfect. And so finding these abstract, weird, difficult questions will help you practice where there isn't a specified method. There isn't something where, oh, I just take an equation, put it there, put the numbers in, and I get an answer. So be careful with questions like these. This is why this is a 4-mark question. Let's go back and let's see where we scored the marks. To define the radioactive decay constant, if I say probability of a decay occurring, great, but it's not just that, it's the probability per unit time. It's measured in per second. Both of these are required for the 2 marks. Next, in the derivation of the decay constant, you need to know this derivation, you need to know how to get there. You don't need to know to memorize the steps. Know where to start and know how to get rid of the n's in this equation. Since you have lambda t and a constant, there's no n's. Show us how to get rid of the n's. That happens by the substitution. Half the particles are left when the half-life t half has occurred. So you get a mark there. Taking natural logs, doing correct mathematics scores you the 2nd mark. And so the reason it's not 3 marks is because the form of the equation is given. They tell you what the final answer should look like. If you don't get it correct here, you can still use it in subsequent problems. That's the good thing. The next one was quite a significant problem. Find the volume of water in the container. And so, if you calculated what the activity should have been, then you would have done some correct substitutions, which have scored you 1, and you would have found an activity of the sample after 36 hours. Even though it's not the final answer, you scored 2 out of 4 marks. Now I need to double down, I need to find the volume of the water. So by doing this correct ratio analysis, and again correct substitution, which wouldn't have been wrong if you did the mathematics correctly, would leave you with an accurate final answer, and a mark for accuracy would be the 4th mark. So long, complicated, abstract problems like this are generally worth more marks. And so the more you practice these kinds of questions, the easier they will become. I'm not saying that you will see a question that you've done before, but it's likely that the techniques that you use to solve these kinds of problems will be more apparent to you. Looking at a question will take you less time before you actually put pen to paper, which is what you want. You cannot spend 10 minutes solving a 4-mark problem. 10, 15, even longer, unless you saved a lot of time from other questions. But guess what? There's going to be more than one of these kinds of questions in an exam. Okay, so that was the end, or this is the end of the video, the end of the problem solving. Like I said, there's many more questions that you could encounter. It is literally up to you to find them, to hunt them down, to open them up, to practice, and leave the mark schemes well alone. The mark schemes are a guide for markers. Solve as many as you can, and then use the mark scheme as a guide. If your teacher does not help you, or you cannot find help anywhere, use the mark schemes as a guide, but remember, they are simply that, and they are meant for the markers and not for you. The more you solve problems like these, the easier the technique becomes, and the better you get at doing it. I hope this video has been helpful. I'll see you next time with maybe another crash course on the next topic, or another problem solving video. So I'll see you next time. I'm Mr. K and this is Everything is Relative. Until next time, goodbye.